Hello, people. I'm just going to make a little bit of green tea for a little bit of caffeine. We're going to hopefully get some more gains. Why are you going to give up on being a dev? I don't know what being a dev means. Does that mean you star in the TV show Devs? What does it mean? Hmm. So I've been sort of taking a break a little bit, but I've also been just doing some cleanups and restructurings that did not involve making gains. So I guess I was making gains in code cleanliness or something, but we did not decrease our Weissman score. In fact, it might have gone just a little bit. We're at 357,636. Yeah, okay, that's about what we had. We'll see if we can make more gains. The x64 debug info is still corrupt for some reason. You know, I kind of just want to look at the output here for a bit. Let me put that in a file. I have some more notes about gains, but honestly, we did a lot of them. Today was a good gains day. Oh. So there's this pull small data from R value happens a lot. I'm not sure why. That's one of the things I was looking at today. Sure happens a lot. Oh boy, I'm yawning. So let's just see like what line this is happening. Ha ha ha. 799, right? So we're Okay, we're calling max on highest water. Highest water is a global. So we're loading from a global. I mean, honestly, woof. Like just having an equivalent of this segment Lee here would be a good instruction to have. Because then we wouldn't have all these frickin' Lees. Pause on gains. I don't think you people understand what we are doing here today. Coffee is for gainers. A always, B, G gaining. Always be gaining. Always be gaining. All right. So I want to know. So I think it's coming from here. Yeah, okay, we're going to make a segment move command in the bytecode. And we're going to see if we can finish it. Segment move comes from R, or it puts in R. Segment in O, offset in big constant. Okay, segment move. Segment move. All right, segment Lee does this. I guess we call that a load. Let's call it segment load plus offset, just for consistency. Okay, so this is a problem. It's just so sometimes, like the things that you want in order for compile time execution to run quickly are different from the things that you want for compiled code to run quickly. And the thing that I was about to do would be fine for compiled code, but not so great for compile time execution. And I gotta think about what people want. You know? So the problem is if I want to put just a segment index and then an address in that segment. Right? Because at runtime, that segment is mapped to linearly. The problem is during compile time, because we have execution, while the segment is growing, the segment is not a linear piece of memory. And so you don't have how would you say? You don't have an easy way to find the address of the thing. Now, segment Lee here just stores the frickin' stack allocation, but that's because that has information So the problem is this thing is huge because it's a pointer, so it takes up a lot of the space for bytecode instruction. We don't want to make the instructions bigger. This would solve our problem because individual allocations are guaranteed to be packed together for compile time execution. I mean, we could have some ancillary data structure, like we could have an integer handle to allocations and there's a table or something, but I'm too tired to do that kind of thing tonight. This stream might involve zero gains and me just being tired thinking about things. So anyway, for the compile time code, we say, okay, what's the symbol index in the executable, right? And then we do the pointer load from the base address. Or This should be called emit.ly probably. Anyway, so you see my problem here. Segment plus index should be all I need. But that's going to make compile time execution run slow, and there's a lot of these instructions. So it would be trivial to make the, or not trivial, but it would not be that hard to make the gains that we want to make in terms of Weisman score. But we would be losing in execution speed more than I am necessarily willing to give up. Now that said, we could have a limited offset because the segment index is only like 2 frickin' bits right now. So we could like mask that off. The problem is even 32 bits of offset is not really enough. Because you could easily have a 4 gigabyte array. I mean, people do that all the time. Well, I actually don't know. Your executable probably wouldn't load if you put that in your data segment. So maybe it's actually fine. How big are data segments allowed to get these days? Never in your life did you do a 4 gigabyte array? Sure, but 15 years from now, is someone going to want to do a 4 gigabyte array? Probably. Unless computers just get so slow that that's inconceivable to do anything that big. Okay, I could actually, if the linear allocation has enough information to trace back, which I think it actually does. Right, I forgot I was going to look this up. Because I'm tired enough that my brain is out of brains. So linear allocation, it doesn't. Does not. I mean, I guess we already have this limit. So maybe I just don't worry about it and I say, hey, there's a 2 gigabyte limit right now. So I could add an extra pointer to this. The problem is that starts making this pretty fat. But we could do that. We could add an extra pointer to this that goes back to the linear data structure. How big is it? It's 8, 16, 32 bytes right now. So we'd be going from 32 bytes to 40 bytes. Problem is every global variable has one of these. So if you make a program with 10,000 global variables in separate declarations, well, yeah, I guess this is fine, actually. We're going to do this experiment. Okay, so what do I need? So then we have this linear allocation pointer just like in the Lie. And we just need offset within that. That's pretty easy. So the offset can, yeah, okay, we're going to do this. Linear data reside inside. Okay. Like what? This looks like it's the same. This looks like it's a port of old code and doesn't make sense anymore. Okay, that's LLVM. It's mostly for LLVM, which, again, is kind of irresponsible. Okay. Let's make a hash table, bro. But it's not that big. So we probably need the allocation flags, alignment. Meh, we could use that. We don't have to have it. Actually, no, we'd rather not have it. Final Fantasy, the index within. So I keep seeing all these things that I can clean up. But that's fun. It's just fun. Okay, so actually we want new data segment allocate. New data segment allocate. Okay. So we do a linear allocate. Okay. Great. GCC takes 14 seconds to compile a program with a 1 gigabyte static initialized array. Is it all zeros? GCC failed to compile 4 gigs, failing to resolve relocations. Yeah, I mean, I do not know that the object file format provides big enough indices. It might. Like Dwarf might, I guess. Because like Dwarf has the weirdo configurable size integers. That's probably the reason why Linux is so damn slow. Windows, I don't think even has that. All right, so we're going to do this way. Okay, segment load plus offset. Why is integer add plus constant in here? That should not be near the memory stuff. Okay, so you have segmently, which is fast because we just have a frickin' pointer. We have stackly. We have segment load plus offset, which is going to look like segmently actually. Actually, we're going to do this. We're going to go. We're going to assert segment not equal to null. Okay, and then we're actually going to. Oh, never mind. We actually don't care about this yet. We're going to do this. And then okay. So I just want to do this. So segment load plus offset is going to be within a particular allocation. and then we'll work that out. Okay. So actually, we could make this an inline. Let's just see if I don't need a thing. Get number flags. All right. Oh. Okay. Well, great. But we want that plus linear allocation is in big constant. The offset is in O. Okay. All right, let's just make that compile. Make sure it runs. We're not using any of this yet. Whoops. So, yay. Great. Now we want to make an attempt to implement this here. So segment load plus offset in x64 is going to be, we want this segment. This segment is going to have an address okay. Get symbol writer and Lee, what is it called? Lee segment. Oh, just this. All right, that's going to be that. And we'll finish that in a bit because we want to go up here and do this. We're going to go inline S32 get symbol obj writer segment. Okay. Get symbol blah. Get symbol blah. Okay, once we get that symbol, we load some stuff. Emit pointer load here says symbol index and offset. Yeah, this is really a load effective address. It sounds like it's loading out of memory. So we want to say we're not super worried about x64 code gen quality right now. So we're not going to try to optimize this totally. That comes later, one step at a time. So we're going to do this. And we're going to say load machine register. No, that's not what we want. We want to get a free register. Oh, we got a free register. It's called reg. Oh. L value. L value. Then we want to move 64 indirect. Reg. Reg. BC arrow offset. Into register. All right. And then we store machine register. Okay. Who knows? Oh, this wasn't so data segment doesn't have a least segment index yet. Okay. Got to set those. Okay. Do you think there are enough depessimizations left to hit 336K? Who knows? There might be. I am always finding more gains than I expected. Right? Okay. Okay. Yeah. Auto differs in levels of indirection from linear allocations. What? It's probably just emit pointer load. Oh, no, that's it. What is going on? How are the error messages so damn bad? Let's just call it reg. Does the same thing... It's the same thing I do up here, guys. Literally the same. This is going to be one of those things where the problem is a totally different problem. Does anyone see the problem? It just placed uninitialized array in the BSS. Isn't that okay? If you didn't specify any data, it should be fine in the BSS. SA is declared twice. Oh, well, why don't they frickin' say redeclaration of variable? Thank you. I realize it's not related to what I'm doing. I'm just poking over and trying to figure it out. Okay. In theory, maybe if I generate this instruction, it'll work, maybe. Probably not. But let's try it. I blew away my output.txt. Pull small r value. Right. This was where we were. Okay, so I'm going to no check in this. This is just generally code that refers to global data. We're going to flip-flop it around. I'm a flip-flopper. I'm a flip-flopper. Okay. We're going to do this. And then instead of this, we're going to say result equals okay. We put that into result. What is result? Okay, we'll refactor this and clean it up later, but the point being, if this is small and we know where it is, we get it from where it is. Okay. Okay. Well, the compile time execution worked. We did get some gains. We didn't get as much in terms of gains as I wanted, but I think that's because there are other places in the source code where we can do this. This isn't the only one. Problem, I haven't done this for LLVM yet. So, well, let's run x64 tests. Well, let's run this to show you, hey, unknown instruction in LLVM, but x64 is handling it. Okay. Okay. So we'll deal with this mess later. So we do the load effective address, and wait, what just happened? I was like deleting this, which would have made me sad. Segment load plus offset. We do a bunch of stuff, and then we create the load. Okay. So we do the load effective address. We're going to node check in this. We do the load effective address, and then the segment is actually SA arrow owning segment.lee segment index, something like that. Calling it Lee segment index doesn't make sense anymore. Just making sure we compile. Oh, arrow. Okay. So we do the gap. And then we add the offset. We need that offset parameter. I'm going to make sure I see that. And, well, okay. Actually, let's put this down here so that we won't miss it. We get the offset. We don't use index B. What are you talking about? We want to say gep gets casted to the target register's type. And then we create a load. Create load from gep. And then something like that. I don't know how to do LLVM. All right. Whoops, not x64, LLVM. All right, great. While those tests are running, our bytecode dumper does not know this instruction. So we want segment load plus offset. That's going to be move anyway. We'll think about that. But in the meantime, we want to draw this as a move, and then there, SA owning segment, leave segment index. Okay. Did I remember to add the offset here? Yes. All right. Well, now let's, well, first let's get our Weissman score again. Actually, let's compile. We need to compile because, see, it didn't know how to print it. It knew the name of the thing, but it didn't know how to print it. So, so our Weissman score is, it wasn't that good. 356, 349, 356, 372. I mean, that's an improvement, Don't get me wrong, but I was hoping for more. But there are trolling is bannable. Like, okay, guys, here's the thing about this channel. Things that actually annoy me or distracting me while I'm trying to work are bannable because I have a lot of work to do. And if streaming interferes with that, then I will stop. So that's just how it is. Okay. So let's put this into a file. Or maybe I'll go subscription only. Yeah, if we can get a Weissman score of minus 9,000, that would be great. All right. So we have more pull small R value from L value, but not nearly as many. We have a lot of Varargs arrays, honestly. Wait. We're leeing. Do we use V26? Yes. All right. Well, that's great. This is a case where actually we want to know that we have this value active and use it instead. Anyway, so we have variable names listed again, which is useful. If we're only reading from them, we do not have to do the lee. That's great. I really did expect more gains from that, actually. Now, we can do the same thing with stack stuff. But I don't see a lot of stack lees here. But we do a lot of things. So we do stack lee and then add int and stuff. Even this, the first step is to combine those. And then we can make a stack move instruction. We sure have a lot of assigned local declaration to value register copies, which generally indicate that we didn't successfully do a placement, I guess. This has lots of Stackleys. We could get more gains by doing a segment store, just like we have a segment load. I don't know if that's easily, well, anyway. Does plug register? Plug register. Plug register already does this if placement is null. All right, let me just test that I could do that. That's a few lines of code gains right there. Whoops. I keep destroying the output file, so I'm just going to let it run. And now we'll run it without the output so we can see. We should check in these gains, assuming that this works, because we haven't checked in a little bit. It might be nice to also write the dump stuff out into a file in the build folder. Here is what I am thinking. I haven't totally put this in yet, but I did off stream the other day. So dump used to literally just be printf to standard out, right? Now it actually goes into a buffer that we then print. So I could put it into files or whatever. But what I'm thinking would be best is if your metaprogram can call like compiler, give me the dump for this function, and then you can just do whatever you want with it. That seems like the best, rather than having them just show up in files. Like if you want to, you know, do stuff. So like the actual little dump directive that I'm just sticking on the functions. I mean, that's nice for my own personal use, but I don't feel like it's super good for what people generally want to do, right? Yeah. So the thing is, in the very long term, after the intermediate representation stabilizes, you could imagine even just getting a data structure with all the information in it. But for now, it's going to be text because it's just changing way too rapidly to try to do a data interface. The question is how to synchronize that, though, because the problem is, like when you get the code type checked message, the function is not compiled yet to bytecode, so you can't actually get the dump at that time, which was maybe the way things flow. That's sort of the most natural time. So you would have to ask for it later, or you would ask for it and it blocks until it shows up, which seems bad. Or you would say, hey, give me the dump for this thing, and then the dump shows up in a message later on. Which seems interesting, I guess. That might be annoying to deal with, but might be fine. Like you would just say, hey, when this thing is compiled, give me the dump, right? Or it could be just more like, well, you just wait. Like if you see a function you're interested in, you just keep that in an array somewhere. And then when you get the compilation complete message, then you could ask for the dump or something. I'm not sure I want to encourage that because that in the long term culturally that leads to slower compiles, right? Because waiting until you're done and then doing a bunch of stuff. But it might be the easiest thing to deal with in the short term. So I don't know. Okay. Anyway, honestly, I'm not really thrilled by that. Oh yeah, there was some stuff we wanted to do. I am not really thrilled by how little those gains were. So this L value placement thing, we don't care, we don't care, we don't care. L value placement is now placement again. And I'm going to run this again, make sure I did not break anything. Let's run the game. We haven't run the game in a little bit. Wait, that said 355,598, which is even a little bit better gains. All right, well, that's what I get for hoping the number was magically lower. All right. Yeah, it's interesting. If you could get the dump and then parse it, you could write your own backend. I don't recommend doing it that way, but it does provide interesting future expansion of the compiler. Okay, I want to look at this add A64B flagged. I think we're going to try to chase some other gains later. This is more of a cleanup, probably. honestly, this code doesn't look super terrible. Except we're doing this a lot. But we could deal with that later. Because it won't reduce the number of instructions, and that's what we are concerned with. So let's look at this line 3014. So this is emit array subscript. So pointer register I don't understand why we are doing this. I mean, this should just work. I think this is kind of old rotten code. So like if I go look at emit array base and count, we handle resizable, view, and fixed. So yeah, this just is. What it is. So we do a bounds check. We omit the base pointer for the array. Oh. If it's a fixed array, we can be more efficient here. Okay, so we're going to keep this little type. But we're not going to actually do it yet. We just want to make this work first. So right. Okay. If we want the L value, we do the add A64B flagged. with the value placement. Okay. If it's an R value, we do this and pull small r value from L value. And is that what we were looking at? Yeah, probably. So we don't want to do that. Again, this is what are my bytecodes called? Load plus offset, right? Vanilla load plus offset. Yes. Load plus offset from the pointer offset register. Fudge. See, here's the problem is somebody might want the address. No, literally. See, this is, oh wait, hold on. This is for if it's an array, element address register. Damn it, bro. Okay. This is another thing we can clean up. But for now, we're just going to deal with it. We're going to say if they want the element address, we're just going to do all this stuff. That's all only for this one case right here that we could probably do differently. So this is a bunch of garbage code that hopefully we're going to get rid of. Okay, great. Otherwise, we load plus offset. Actually, we could compute it separately. Yeah. Anyway, we load plus offset, pointer offset register. And we put that in R value. Do we have R value register? It's a plug right there. Okay. R value okay. Otherwise, we're going to plug right here. We're going to load plus offset BC options equals oh, this is not a constant offset. We can't do this. Can't do it. Okay. You know what? We've screwed with a lot of things. Let's just make sure this still works for a minute. Probably doesn't. Emit array base and count. Array fixed. Array view, array resizable. Oh, I guess none was an option, right? Default, including not an array. Okay. Okay, so if it's not an array, I should read my own code. Okay, if it's a string, we deal with it. All right. All right, so we at least, we got some lines of code gains. If not Weissman score out of that. Okay, I want to get rid of this A64B flagged. I mean, I kind of want binop plus. So why am I not doing that? Because they might be different type sizes. Right, when I do this, it's going to complain that they're different sizes. Yeah. Okay, so at least I know how my system works here. So the question is, do I want this? I think so. Because sine extending B is natural. So instead of calling it B flagged, we're going to call it we're just going to call it we're going to replace A64 B flagged with extend B, because we may eventually want it to work on A's that are not 64 bits. Like, there's no reason why not. It's just, it's a capability of the system that you can have a system generated integer add or subtract that does not require LLVM style annoying casts. And that is just one of the things that we can do. Okay. So okay. Great. That was not gains, but it was learning, and I got to check off the thing, and I got to make it a little more formal. So that's great. So I think assigning to structs is a place where we can get gains. I feel like that's a thing. So like, oh, let's get this back. I took out the dump. Took out the dump. All right. Do we run? We'll check it in if we run. And then we'll go in search of more gains. Dang it. Oh. Ha ha. Okay, we got to fix this. segment load plus offset, we are going to say auto create Lee of helper SA and 0 all right, and why is that? And so segment is going to be this, and we're going to say BC options I hate the abbreviation putter so bad, dude. Is that? Yeah. LLVM. There are no extraneous zero indices in get element pointer. Oh, I forgot to put in the offset. Very bad. Almost broke it. Almost broke it. Okay. Now let's try. No! Dang it. Okay. Wait, no, this isn't right. There's an offset in segment Lee, isn't there? No. Okay. I mean, that sure looks like what we had. Should have checked it in while I was ahead. The array subscript's busted. Um, why am I even looking in this file? Oh my gosh. It's the concatenate function that's busted again. We had exactly this problem before. Like what? What did I do wrong? I mean, should I just Emacs undo back to where I was? And make sure it was broken? And we'll do it all again. Sometimes that's the best thing to do. All right. Ta-da! See, when I really want to go to sleep, I find a way. Life finds a way, as we learned in Jurassic Park. Oh, it's probably... It's probably this. Like, that's probably hosed. Anyway. Okay. Yep, that was the problem. Okay. So I'm going to leave that in there. And then here, we're going to do this. All right. Whoa, Nelly. Nelly. Oh, because we have a comment inside. You can't do that in C++ on television. All right. Well, everybody, it's pretty close to bedtime for me. So I think we're not actually going to get these next gains tonight, but that just means we have gains to get over the weekend. I think. I don't think we did any gains in all that. that was just me getting ready to check in so I could do the gains. Let's not change anything. Getting awfully close to 100K reduction. I suppose that's true. I suppose we might get there. I suppose we might get there. So, just to refresh my memory, when we do array subscripts, here, oh, did I decide that this was not easy? Right, because the... Okay. So the deal is, this subscript function, it's being written in a very dynamic, abstracted way. Where, and this might be fine. This actually might be fine. But the subscript is like in a unknown at compile time, right? Because a lot of the time you're looping and you're subscripting. But if you say like sub 0 or whatever, in theory, that's not bad. We could do something about it, but maybe that's a better thing for the backend optimizer to do. What did I forgot what we were trying to check in. Recent messages. That's probably what it was. No, it's still, oh, better arguments. Right. We can revert that sucker. Boom. Okay. Does the reduction in operations result in game performance increase? Yes, at least in the debug build, which is important. We've definitely gotten noticeable increases in the game speed. And also compile speed, interestingly enough. So like these operations that we're doing are saving, even in our already fast compiler, they're saving more time than they take to perform. And I'm not even trying that hard to do anything clever with them. Do you use a fixed size stack or does it grow and shrink dynamically like Go? The answer is I don't care. I've never needed a dynamic stack in C or C++. I don't know why you would have one. Like, why would you do that? Where is compile speed at? Well, we can't really tell because right now, I mean, we could turn off all the dumps, but I want to leave the dumps on for later so we can keep looking at code. And the problem is the Windows console really slows us down. So we can't see what the compiler speed actually is. With the dumps, we're at 0.75, but it's probably more like 0.64 or less, 0.63. I want to leave the dumps on so that we can see what these things are. You know, at some point, see, we're doing all these like stackleys to assign to globals. I think that would be our next big gain, is to just have a store like that. I might want to reduce. So I made Stackly and Segmently different. But honestly, we could just have that be Segmently and then segment load plus offset and then segment store plus offset. And then those just all handle the stack as one of the segments. I think that's what we're going to do. So that's going to be, you can see here though, we have all these cases where it's like taking the address of a thing, loading some constant, storing the constant into the address of the thing. When we could just load the constant and then move into, data segment plus V132, right? This is sort of like a very RISC processor way of doing it. And the problem is that just doesn't map very well onto current things. That said, you might actually want to do this as the input to an optimizer or something, because if people wanted the address, but like you still want to be able to do the store that way so that you can re-glom it into that. So I think this is probably fine. Why do you use dynamic stack size? Go does it for user space threads, aka Go routines. Oh, right. So they keep the stack very small because if you want like a lot of threads, then they are small unless you need it to be big. Yeah, I mean, that's just not, I don't know. I don't want 100,000 Go routines unless I have 100,000 cores. Like, if I have enough cores to do that work, I've got enough memory for all the cores. Like, it's just not, it doesn't make sense to me. Have I ever needed to adjust the stack size? Not really, no. There might have been once a very long time ago, but it's generally not a problem. Like, in order to run out of stack in C or C++, you have to do heavily recursive code and also have large things on the stack. $100,000 cores. Probably you'll have that in 10 to 12 years on average desktop computer. No, I don't think that's true. So here's the thing. With CPUs, we've gradually been running out of ways to make them faster, right? Like, it became very hard to make the clock faster, right? So we're doing process shrinks still, but process shrinks are now very hard, right? Making the pipeline deeper became very hard. So the one thing we have left is more cores, but that doesn't extend forever either. Like, the further the cores are from each other, the more heat you have to dissipate, the more cores. Like, you have all these problems, and we haven't reached the limit of how many cores yet, but like, we're going to get there before too long. And also, it's harder and harder. The more cores you have, the harder it is for software to use them effectively. So I don't think we're going to have 100,000 core machines. On your PC with Linux, default stack size allocated for new process is 8 megs. Yeah, I think Windows might still be 1 meg, and I still never hit it. Like, 1 meg seems really small, but it's like literally never a problem. All right, everybody. I am probably not going to stream tomorrow morning because I'm taking a nice day break and going on a little trip. But maybe in the evening or maybe Sunday, we will do some more gains. There are gains to be had. For sure. But on it, like, you know, if you look at this, if you look at code like this, it's like, I mean, okay, we could get rid of that instruction and maybe that one, and, you know, but at some point, it's just not that many more instructions to get rid of. Unless, like, you could take it too far. You could start saying, oh, I'm going to design all these bytecode instructions that do like 3 or 4 instruction sequences in one, and then I can minimize. But that's not the goal, right? We're not trying to be absurd about this. We're trying to, for a reasonable set of instructions, we're trying to generate them as best we can in the front end without going insane. And yeah. What's the ratio of performance increase to instruction reduction? I don't know because I have not really been measuring. It seems linear. Actually, there were a couple that were a little bit more than linear. So I think when we did the non-short circuit and OR optimization, I think because that removed hard to predict branches, we got more of a speed win than instruction win, right? But for the most part, it seems roughly proportional, which makes sense to me. All right, everybody. I'm going to sign off for the night. Thank you for coming by. And yeah, I think so. The plan is combine Stackly back into Segmently. All right. And then make segment load plus offset handle the stack as well. Whether we use that, I'm not sure. We'll find a way to use it. And then we'll make a store plus offset. And then that's it. That might be it for the gains for now until, I mean, if we see obvious stupid problems, we could do more gains, but, well, I don't know. We'll spend some time just looking through the code to look for obvious stupid problems, because there really could be obvious stupid problems. All right. Thank you, everybody. See you later. I'm going to bed.